I'm Jeff Pizanson. I am chairing this session, the best session. Our first speaker is Ashton Wiersdorf. He's a PhD student at University of Utah. And he's going to be talking about topics, I think, near and dear to all of us, IEEE floating point and errors. So please.
Thank you. Yeah, I'm Ashton Wiersdorf, and my colleagues and I at the University of Utah have developed some tools to help you track down problems in your floating point code. And our tool set, called FlowFPX, has already proven useful. So we hope that you, too, will find it useful. Imagine that you're a busy scientist doing some numerical work. Now, for some of you, you won't have to imagine that. That's your reality. But for the rest of us, let's all imagine that you're working on doing a heat simulation where you're observing the change in temperature in a slab of metal over time and seen as that animation. All's going well, and you're tweaking some parameters, and then all of a sudden your simulation starts looking a little unhappy. Ah, man. What happened? Where did that hole come from? Well, the answer is NaN happened. What is NaN? NaN stands for not a number, and it's part of the IEEE 754 floating point spec. What is this spec? Well, IEEE 754 standardizes floating point representation and operations across architectures, so it saves us from the pain of having to port every little floating point function that we have to new hardware. And we can rely on some consistent behaviors across all of our platforms. This spec also describes some things called exceptional values, of which NaN is one. What are those? Well, first we need to remember that floating point numbers are a discrete and finite approximation of real numbers. Compared to the continuous real number line, floating point numbers are discrete points along this region. And there's always some gap between the real values that we want and the values that we can represent in floating point. And that gap is error, and that error accumulates throughout your computation. And error, combined with finite representation, means that you get into some crazy situations where we get exceptional values. William Kahan says, an arithmetic exception arises when there is no result that would be acceptable universally. So let's look at what the exceptional values are that we have. There's NaN, what we've seen before, not a number. There's infinity, which is what we get when we exceed our representation capacity, and subnormal values when we underflow. In this talk, though, we're going to be focusing on inf and NaN. Let's drill into NaN. NaN arises when there's no clear mathematical answer to your computation, something nonsensical like dividing 0 by 0, or there are some other ways other than these listed here, like taking the square root or logarithm of a negative number. And once a NaN appears, a NaN will propagate, meaning doing some operation with a NaN will result in a NaN. Like if I have 5 and I add it to NaN, I get a NaN out. I don't get NaN 5. So you might be wondering, why don't we just throw an error in these situations where it doesn't make sense? Well, as Kahan said, that's not necessarily the thing you want to do in every situation. So you need to use code that's tailored to your needs, but properly crafted code isn't always available, right? So hence we have exceptional values that flow through code with a lifetime that we've characterized as follows. At the beginning, we have gens, what we call gens or generations, when an exceptional value comes into being. Once an exceptional value has manifested, then the next phase of its life cycle is called a prop, or a propagation, where that value proceeds through operations, hopefully manifesting in the output like that hole that we saw earlier. And that's nice because we know that something's gone wrong, and we now have a clue that we should go back and try and figure out, find a problem and fix it. But there is one more phase of its life cycle that can occasionally crop up. And instead of manifesting as, say, a hole in a graph or a blob of white on your chart, there are kills, and that is when an exceptional value silently gets swallowed by an operation. Instead of letting us know, it can silently lead our computation down the wrong path. So kills are very risky because our computation can be wrong, and we might not even know it. We'll see an example of when that happens shortly. So let's go back to our graph. So you've got a problem. You've got this hole in your graph. You know something's wrong with the computation. So down the rabbit hole into the bowels of your code. You want to find out where that NaN came from. So you start going through all your source code and going over all your equations with a magnifying glass. But you know that doing this is going to be a lot of work. You're going to have to put like print statements everywhere or some other kind of profiling, and that's going to take a lot of time to do, and then that's going to generate a huge log file that you're going to have to comb through, and that's not fun. And you're just like, this is awful. Like, I don't want to do this. I want to get to my work. I don't want to have to deal with this crummy floating point stuff. And you wouldn't be alone if that's how you feel. We found hundreds of issues in Julia repositories on GitHub that mentioned NaN somewhere in their description. So this is not like you're not alone. It's okay. Other people are suffering with you too. But fortunately, our FlowFPX toolkit comes to the rescue. FlowFPX can save you from that manual work. But you don't have to take our word for it. The folks who have been working on the RxInfer package found themselves in this situation. RxInfer is a Bayesian network inference library. And in issue number 116 on the repository, they said, now, they had a problem, and they said, it is impossible to trace back the origin of the very first NaN without performing a lot of manual work. This limits the ability to debug the code and prevent those NaNs in the first place. Sound relatable? Well, we introduced them to FlowFPX's float tracker tool, and the next day they sent us a message. So I'd like to point out that we never saw any of their code, but they were able to find the NaN on their own. So if you are a busy scientist, please go and try our tool. It works for people other than its creators. So onto our tool set, FlowFPX. FlowFPX can help you solve these problems of tracking down exceptional values, but we also provide tools to help you harden your code so that you're less vulnerable to when those exceptional values can crop up. We use a variety of different technologies to make this work. We lean heavily on Julia's type-based dispatch. We do some fuzzing, and we have stat graphs, and we also do a little bit of flow graph diffing. More on all this later. There are two main components to FlowFPX right now that we'll talk about today. There's float tracker and coalesced stack trace graphs, or CSTG. Float tracker uses Julia's types and overloading to produce stack traces and fuzz programs from the inside out. And CSTG takes the stack traces that float tracker produces, and it can coalesce and diff those stack traces. Now, CSTG is a standalone tool, but it works really well in conjunction with float tracker. Excuse me. And we'll be focusing on float tracker for this talk, as it's written in Julia for Julia programs, and we are at JuliaCon after all. But we'll see a little bit of how CSTG can help us out. And this is a growing tool set, so more in this vein later. Let's take a look at an example. This example was inspired by Nimble et al. There at the archive link. Let's write a function to compute the maximum of a list. We take a list in, we keep track of the biggest seen value, and then we iterate through that list. For every value x in that list, if it is not less than the max seen value, then we swap out the max seen value for that element that we're looking at. And then we'll print out the result. Now, spoiler alert, this NaN in our input list is going to make life interesting. So let's see what happens. Let's go ahead and run this code, and just for sanity's sake, what are we expecting? That's right, it's the number 5. Let's go ahead and fire this off. What? Wait, that's not the maximum value of the list. What happened? Well, we could go back and like try and figure this out manually the way we're used to, but let's call float tracker and ask for some help. So the first step to using float tracker is to say using float tracker. And then you wrap the input in our tracked float 32 type. And float tracker builds up logs and it flushes them periodically to file, but just at the end, just to be safe, let's just ask float tracker to finish up tidying those logs. Okay, so with these few modifications, we rerun our code, get the same result, but this time we get some log files. We get 3 log files, one for each kind of event in an exceptional values lifetime. As a refresher, this is how we categorize those events. If there's no nan in the arguments, but a nan in the output, then that's a gen because a nan's been brought forth into being, and so that event gets logged in the gen file, and so on with props. Nan flows in, nan flows out, and a kill, nan flows in, but no nan flows out. And when we run this, you'll notice that we get some kill logs. And that should always send up a little bit of a red flag. It's like, maybe there's something going on there. So let's take a look at the kill logs, and this is what we see. The kill logs give us, well, all the logs actually, but they give us a stack trace of where that event happened. And the kill logs give us a stack trace of where a nan was killed. And it looks like the less than function is the culprit here. And the arguments are nan and 4. This is a kill, of course, because a nan goes into the comparison, but it doesn't come out. The thing is that works both ways. It doesn't matter which way you compare against a nan, you always get false. That's part of the spec, by the way. With those clues from float tracker in mind, let's step through this carefully. So 1 is going to be our first max scene value. And then we move on to 5. We compare with the max scene, and 5 is not less than 1. So we swap. And 5 is now our max scene. Next, we move on to 4. 4 is less than 5, so we don't swap. And now something interesting when it comes to nan. Because we're comparing against a nan, nan is not less than 5, and so we swap the max scene for a nan. And then when we move on to the next value with 4, 4 is also not less than nan, so we swap that out for 4. So there's our error right there. That's what happened. Now, the correct thing to do in a situation like this would be to propagate or otherwise guard against that nan. That depends on your situation. But the nice thing is float tracker has given us clues as to where to look. So as a recap, to use float tracker, you simply require float tracker, wrap your inputs with tracked float types, and then flush any buffered logs that haven't been flushed to file already. Let's take a look at another example. There's this library called Shallow Waters by Milan Kluver, who happens to be giving a presentation, I think, in that room over there right now on climate modeling. So thanks, Milan. Shallow Waters is a Julia library that lets you take a mesh of a sea floor and then run a time series simulation to get the speed of currents in the water over that sea floor. And like many simulations, Shallow Waters operates by modeling one time frame after another. And there's a parameter called the CFL parameter that controls how fast information propagates through a time series simulation. Small CFL values give you accurate simulations, but slower renders. And big CFL values give you faster renders, but you run the risk of getting some instability into your simulation. And what does instability look like? Well, here's an example of some Shallow Waters output with a modest CFL parameter. But if you dial up the CFL parameter a little too high, you get something that looks like that. And, all that white is where nan has crept into the computation and come out into the output as a whole. So let's say we're at this situation here, and let's call float tracker to see if we can figure out where those nans are coming from. And in this case, we want to try and drill down to concrete values as fast as we can, and to hand that off to a domain expert to figure out how to fix our simulation. So just like before, we run float tracker and we get log files for every different kind of event. And this time, because we're trying to figure out where those nans came from, we're going to take a look at the gen logs. And this file comes in at the petite weight of 3.1 megabytes. That is a lot of logs to sift through. Fortunately, FlowFPX has another tool called CSTG to help us out with this. So what CSTG does is it summarizes flows or groups of stack traces for us, exactly what float tracker produces. And this builds off of some of the work of STAT from the Lawrence Livermore National Laboratory. So what does CSTG do? Well, suppose I have a file full of stack traces like that. Here I have 5 stack traces with 4 frames each. CSTG draws a graph, one node for every frame, and then as it proceeds through the groups of stack traces, it adds or increments an edge between nodes for every pair of consecutive stack frames. So this gives you a glanceable view of what the most heavily trodden areas in your code are, though the thin areas are still worth investigating. So we run CSTG on our gen logs, and we get something that looks like this. It summarizes all those megabytes into a nice little graph where the thick arrows and high numbers mean that those frames showed up next to each other quite a bit. So, and we read these graphs from bottom up. We see that down there in the bottom right that most of the problems came from that addition inside of the continuity itself. So let's go into that log file, but now we know what we're looking for. We don't have to try and comb through all those logs and make sense of it ourselves. So we pop open that file, and here's what we see. Okay, so there's a NAND gen, and it looks like the arguments to addition are infinity and negative infinity right there. And that is one of the nonsensical computations that is known to yield a NAN. But that begs the question, of course, where did that infinity come from? Well, we can call float tracker again and get some help with this. So here is the CSTG for the infinity gens. And it looks like almost all of the infinity gens are coming from this exponent. So let's go ahead and look at the logs. And here's what we got. So I'm going to pull out the salient values again. Negative 1.5 times 10 to the 31st squared. Okay, that is definitely going to blow your 32-bit representation out of the shallow water. And now we're out of exception land. Woohoo! So we've got concrete values that we can hand off to a domain expert now. Float tracker gave us all these nice logs, and with CSTG, we were able to summarize them very nicely into a glanceable view to help us figure out where those problems were coming from. Now you might wonder, okay, cool. So I've got this summary of where of what like the heavily trodden areas of my code are, but how does that flow change over time? Because you might have one little thing that goes wrong at the beginning of your execution, and then your code just kind of spirals out of control for who knows how many iterations. So what we can do is we took our CSTG gen logs and we just cut them at the 10% mark into 2 files, part 1 for the first 10% of the execution, and then part 2 for the last 90% of the execution. And then we generated the CSTGs for both of these. And you know, we could look at them and compare to see what's different, but that can be a little hard to read, and if your CSTGs get big, that gets unwieldy fast. But CSTG gives us the ability to diff graphs, and so we diffed those 2 graphs that you just saw, and this is what we get. Those green arrows are flows that are new in the latter 90% of the execution, and the red flows are the red arrows are flows that were present in the first 10%, but not in the latter 90%. This is just another clue to help you determine what's going on inside of your code. Let's talk a little bit about fuzzing now. Why might you want to fuzz your floating point code? Well, here's a video of a robot Formula 1 car crashing straight into a wall. What happened? Well, what happened was that a NAN got sent from a faulty sensor sent a NAN over the sensor bus. And the code for the steering column didn't know how to handle that. It picked it up, it just saw it come across the bus and was like, oh, I'm going to go into my default state. And its default state happened to be a hard turn to the right. And so when the command to go goes to the motor, it's like, okay, I can go now, but the steering column's like, I still don't know what I'm supposed to do, so I'm going to stay hard turn to the right, and boom, right into the wall. So, you know, if NAN doesn't show up in testing, we might wonder, how can we be confident that our code won't crash, sometimes literally, in production when a NAN might actually show up? So let's call Float Tracker again and ask for some help. So we started fuzzing this library called N-Body Simulator, and it does an N-body simulation of massive bodies. We turned the fuzzer on, and we got nothing, like zilch. There were no floating point operations anywhere in this code. It turns out that N-Body Simulator offloaded all of the heavy work onto the ordinary diffie-q library, and that's where all the math actually happens. So we said, no problem, and we'll expand our scope to the ordinary diffie-q library. So here's how we configure our fuzzer. Every time you do a floating point operation, you roll a two-sided die, also known as a coin. And if you crit fail, you inject a NAN. But we only do this inside of the N-Body Simulator or ordinary diffie-q libraries. I don't want to really fuzz the standard library. I'm not interested in that right now. And then we save that fuzzing run to an injection file. This is the full set of operations that you can use to configure your fuzzer. You can control how many NANs you inject. If you just want to murder your code with NANs, you can do that. We just default to 1. And then we also give you a little bit more fine-grained control over where and when you inject NANs. So with this injection recording, fuzzing includes some randomness, and recording that fuzz session lets us replay that fuzzing session as many times as we'd like to inspect an interesting occurrence, or we can repeat those injections after we harden our code to make sure that they've actually done something. So we ran our fuzzer, and we got we noticed that the program said, notice some instability, I'm going to stop now. But it didn't stop. It went to an infinite loop. We're like, huh, interesting. And we also saw some kill logs come up, and we're like, very interesting. And so we looked at the kill logs, and we noticed here that there was something inside of this solve.jl file. So let's go and look at that right now. Here's a smoking gun as to where our bug came from. There are two while loops in this function. The first is this big while loop that iterates until the t-stops list is empty. And then there's this inner loop that on every iteration is supposed to pop something off of that t-stops list. But it turns out that this tdir variable right here was nan. And as we saw before, any comparison with the nan is false. And so this inner loop never ran. Consequently, the outer loop never stopped because nothing ever got pulled off of the t-stops list. So we found a vulnerable place, and you can see our bug report here on GitHub if you so desire. Let's get down to the nitty-gritty of how we did this. Did we manage did we write a custom Julia kernel? No, we actually did this all entirely inside of userland, thanks to Julia's magic. Our first step was to take all of Julia's floating point types and create our own tracked float wrapper around that. A tracked float is a subtype of an abstract tracked float, which is a subtype of an abstract float. So anywhere where you can use a float, our tracked float is an acceptable thing to stuff in there. With these types in hand, we overloaded all the operators, and here's an example of how we overloaded addition for the tracked float 32 type. We just unwrap both of the tracked floats, add them, check to see if there was anything interesting that happened, and log if something interesting did happen, and then return the result wrapped in a new tracked float 32. So we're making heavy use of the magic of Julia's type dispatch to make this work. Of course, this would be pretty hard to maintain if we did this by hand, right? There are 3 different tracked float types, and there are dozens and dozens of operators in base, and like, who would want to do that? You have a question? Parametric type. It's a good question. Can we take it offline? Thank you. Thank you. So yeah, you might be wondering, like, how do we make this all work? Or like, that's a lot of code to write, but fortunately, Julia also has macros. So this approach was inspired by Milan Kluver's Sherlock's library. Thanks again, Milan. Well, we essentially just have two big for loops. We have an outer one that loops through each of our types. And then for each of the types, we loop through all of the operators, like plus, subtraction, division, etc. Our code works out to be about 218 lines of code, and that's like not counting whites. That's including white space and comments. So this isn't like a massage number or anything. This is like the length of our file, and that generates about 645 function variants. Without the macros, we would have ended up writing about 4 lines per function or 8,000 lines of code. So this is over a 10x reduction in code size. So thank you, macros. Another nice thing is you can write your own overrides too. This is something we encountered with some frequency. There'd be some fancy function somewhere that would dispatch directly on a float 16 or a float 32 or some brand new type that was specific to that library. And you can write your own overrides whenever you want to work with a track float type. So here's an example from one project that uses this special for-diff dual type. Without modifying float tracker or the library of interest, we were able to extend float tracker to support the library's custom data type. So type dispatch is really awesome and really powerful. In conclusion, I hope you remember that tracking down instances of nan and infinity does not have to be painful. Float tracker does it all for you automatically. Float tracker and CSTG are also ready for you to use. You can find them wherever fine software can be downloaded. By that, I mean like GitHub and JuliaHub. We had a lot of fun making this work with Julia's type dispatch. It's a powerful paradigm. But the most important thing that I hope you remember is if there's something strange in your floating point, who are you going to call? Float tracker. Thank you.
All right, thank you very much. You know you've done a good job with the finish of the talk if I don't have to ask people to applaud, but they just do spontaneously. We have time for a couple of questions. You can call on people, and I will repeat the question.
Very good question. Can I ask FlowFPX, flow tracker, to track a separate value that isn't and so if I have some code running, then I know if it crosses like 10 to the 16th or something, that's already bad enough. Could I ask it to, instead of tracking nan, track the separate value?
All right, so the question is, can you track something other than nan or inf? Like if you're interested in values crossing a certain specified threshold, for example.
We don't have a way to easily do that right now, but it's not hard to extend that. And so maybe if that's a concern that lots of people have, then we'll make that. When I came onto the project, it was just nan, and I added an inf in like a day. So there's no technical reason why we couldn't do that.
And I have a question, which is, can you comment on the overhead of this? Like if you're running something like shallow water, what's the slowdown?
Yeah, let's see. I actually have numbers for that exact thing. So it's big. So if you run shallow waters without a nan, it runs in about 3 seconds. If it gets a nan, it aborts in less than a second. If you turn on float tracker and get a nan, it's like it runs for over a minute. It's like a 9,000 times slowdown. Most of that overhead comes from asking Julia for its stack traces. And it does that as late in the game as possible. So if you filter the event types and limit the number of events logged, then you can really cut that down. So like if we just say, hey, float tracker, only log the first 100 gen events, for example, then the overhead goes way, way down. For overhead, running valgrind gives you about a 100 times slowdown. So just remember, this is not a production tool. Like it's a profiler. You don't run this on your production code, but it's not so prohibitive that it's infeasible. It works and it's practical.
Yeah, I was thinking that the feature of being able to specify in what packages you're interested in was going to be the slow one, because you have to look at the stack trace every time, right, to do that. Yeah. Yeah, sorry about that.
Yeah. That's only on fuzzing, though. So
One more quick question, maybe?
yeah, okay.
So what happens if my program is like a bunch of Julia and Mark's code, and then I call into a black box C solver, and then I do a bunch of other Julia code? Is this package able to kind of manage that?
Yeah, the question is, what if there is a black box C library in the call chain somewhere?
That's a good question. But yeah, like calling a GPU. So FlowFPX does have some tools to help with some situations around that. I don't know exactly. We can talk more offline if you're interested, and I'm sure there's a way. Where there's a will, there's a way. Okay.
All right, yeah, one more quick question.
Okay.
Really quick.
Can flow tracker can track the land not in the Julia code, but other code in the shared library, like the C code and functions in the shared library. If the land is happening, that can
Same question, basically, not non-Julia code. Yeah, in the call chain. I think same question.
No, its focuses on nans coming from Julia code, but you would be able to see that nan pop up. You would get some trace of where it's coming from still. Like you'd be able to watch its propagation. So.
Possible to like note if you've got a tract? Like would the propagations be tracked?
Yes, you can turn that on. It's fairly expensive, and so by default they're off. But yes, that is something that we do track. There's the gens, props, and fills.
And the props would be tracked even if it came from a black box C code?
Yes, yeah. It would have to run into another track. There are technical details, but the short of it is yes, we can find a way to make that happen. So.
All right, we've got to move to the next talk.
Okay.
Which is Lilith. Thank you again.